Hello everyone, welcome to this training video. My name is Daniel Nangelo. In today's training video, we will be talking about various geostatistical techniques, especially when you are working with the data and you want to analyze and also interpret the findings. I usually say that for any analyst, it's very important to just understand that your knowledge of how a particular GIS software works or how a particular statistical packages work is not enough. Rather, it is very important to understand the various field or the various data that you are working with. If you are working in the humanitarian sector, if you are working in agriculture, if you are working in WASH, if you are working in food security and nutrition, or if you are working in health, these are the four spheres. These are the four spheres of the sphere project. Now, having knowledge of these spheres is usually very important for any analyst if they want to achieve or to come up with the results and analyze data properly, so that they have results that are targeted and that are informed and that will be used to make better intervention decisions. In today's training video, I'll not be looking at every geostatistical technique because I have discussed it in my previous video, and this is why I say that if you are joining us for the very first time, then I recommend that you watch our previous video on the theme geostatistics. For today, we'll be looking at interpolation. Welcome, and I hope you learned something new today. So what is geostatistics? So in a nutshell, geostatistics basically is a branch of statistics that analyzes and predicts values associated with spatial or spatio-temporal phenomena. And so that you just understand that many of these geostatistical tools were originally developed as practical means to describe spatial patterns and interpolate values for locations where samples had not been taken. And we will talk about interpolation as we progress, but one of the key themes or one of the key concepts I usually like my students or participants to understand is that in geography, we usually make the assumption that things that are close to one another are more alike than those that are further apart. This is to mean that the similarity increases as these things become closer, and also the similarity will decrease as they grow further apart. Now, the assumption that things or phenomena that are geographically or spatially close together are more similar than those that are further apart. For example, this can be seen especially from air pollution from a factory. Now, given the example of a factory, air pollution is more likely to be more concentrated within the factory vicinity and the immediate surrounding areas, but the pollution concentration will decrease as one moves further away from the factory. Similarly, air and noise pollution will be high in areas next or adjacent to major transport routes, such as roads and marine waterways, but will decrease as one moves away. Interpolation is a process that utilizes measured values taken from non-sample locations and uses those values to estimate or predict values of unsampled locations. For example, data from 3 rainfall stations can be interpolated to predict the rainfall of the surrounding location. Generally, we use interpolation to predict the average aerial rainfall of the administrative area or study area. Similarly, we can use data from non-sample location to derive estimate elevation data for the surrounding areas. The same data can be interpolated to generate a DEM from the point data. A soil scientist uses the soil data from sample location to predict soil values for the surrounding locations, which can be soil type, soil humidity, temperature, soil pH, soil nutrient levels such as potassium and phosphorus levels in the soil. Now, interpolation is very handy, especially when an analyst is working with an extensive geographic area, or when it was almost impossible to adequately get samples from the study area. Now, as an analyst, you need to appreciate that interpolation methods differ based on the underlying assumptions, data requirements, and capabilities to generate different types of output. For example, predicted values as well as errors, or what we call uncertainties associated with them. Now, for this interpolation, there are various algorithms within QGIS which we've said that we've been using for this particular trainings because it's open source. We have a number of algorithms that are tied to interpolation, but for this particular training video, we'll be making use of the inverse distance weighted algorithm within QGIS. So, guys, hang on and let's progress. With me here, I have rainfall stations. That is the point data, the ones that are in blue. And this is my study area, and these are the various districts within the study area. So, this area is fairly huge. It's a region, and we have also districts. So we have 11 rainfall stations and 14 districts. One will argue that 11 rainfall station is not enough to predict, or one rainfall station might not be enough to predict the rainfall of an entire district. I also agree with that, because if you look at how the rainfall station at the GPS location of this particular rainfall station, the rainfall for this particular area might not necessarily influence the entire rainfall of this particular area. We also have areas that do not have rainfall stations, like we have this, and all that. Now, remember the concept that things that are close to each other are more similar, and the similarity decreases as one moves further away. Now, this is a concept that we are basically employing in geostatistics. So, as a participant or as a student of geography or geostatistics, these are the things that you need to understand. Now, using the interpolation technique, we are going to use rainfall values from these 11 rainfall stations to predict rainfall values for these 14 districts. Yes, I know we have districts that do not have a rainfall station. Now, the assumption is that the rainfall for this particular area might be influenced by this rainfall station and by this rainfall station. The rainfall for this particular area, this particular district, might be influenced either by this, or might be a contribution of a rainfall from this, and this for this particular district. The same will apply to all the districts. So, let us progress. Now, this is my data set for the rainfall stations which you are currently seeing here. Alright? So, what we are going to do, we are going to run the inverse distance weighted algorithm. And I'm assuming that you're already in QGIS, so you need to go to Processing, Toolbox. Then within the toolbox, you're going to type within the search bar, the search box, you're going to type Interpolate. And you should be able to see IDW Interpolation, which basically stands for inverse distance weighted interpolation. So I'm going to click on it. And for my vector layer, now one thing that you need to understand, before you run the IDW algorithm, you need to make sure that the two datasets or the datasets that you are working with are in UTM, are in the same UTM or coordinate system, projected coordinate system. Now for my case, if you go to this particular rainfall station layer, you can see that I have mine at WGS UTM zone 37N, which is projected. The same, it is the same with the district dataset, that is WGS 84 UTM zone 37N, and all of them are shape files. So before you start your analysis, just make sure it is like that. Then you go to Processing, then you select Interpolate, and we're interested with the one for interpolation. Now we say that there are many algorithms for interpolation. We can see that we have heat map, we have the IDW, we have line density, tin interpolation, and many others that we are not, that are not purposed, or that were not purposed for this particular training video. Now we need to double click on IDW interpolation. And within here, you can see that we have a window. Now, our input layer, our input vector layer is going to be the rainfall stations. Then we need to select what is the attribute. Now, before we go to that attribute, it's always good to understand your data. So within the attribute table for my rainfall stations, I have the station name, I have the latitude and longitude, I have the class, I have the rainfall long term, mean. Then I have this other data. For my case, I'm only interested with this data, right? Now for me to perform anything on this particular data, it has to be numeric. How do I know that it's numeric? I just technically just go to layer properties, then I select fields. Now I'm interested with long term, so you can see here that it's 1, 2. 1, 2 basically tells you that that particular data that has been stored there is numeric. Under type, you can see it's still double. Under type name, you can still see it's real. Real is a data type within QGIS that stores numeric data. So that is that. I can close now this, then come here and select that I'm interested in interpolating data stored under RF-LTM. After I've done that, the next item is to click on plus. We can use break lines, structure lines, or points. For my case, I'm just going to use points. Under the extend, this is where now it gets interesting. If you look at my rainfall data, there are those rainfall stations that are outside my study area. Then for me to just make sure that everything is okay, I'll need to just make sure that I zoom out so that I'm able to see both my data for interpolation and study area are visualized simultaneously on my map area here. After I've done that, I'll still come back to my interpolation window. Under extend, I'm going to pick and say calculate from map canvas extend. Now for this to work, make sure that the on the fly projection has been set to the same coordinate, to the same projected coordinate system as your data sets here. So I can see mine. So for those who don't know, you can just click here and you'll come here and assign, for our case is zone 37M, and click apply, then OK. Then you'll come here and select calculate, use map canvas extend, like that. Now for those who can remember from my previous videos on methodologies and methodologies in analysis in geostatistics, we said if you have a raster data set, then and you want to compare them or you want to analyze them, they need to have the same resolution. And when we talk about resolution, we are talking about the pixel size has to be the same. Now from this data, I'll be working with the data for NDVI, I'll be working with the data for land cover, land use change, and these data sets have a pixel value or a pixel size of 30 meters. So to be on the safe size, I'm going to use under pixel size, I'm going to assign a pixel size of 30 meters. Why is it 30 meters? Is because our coordinate system, the projected coordinate system usually represent values in meters. So when I input here 30, it means 30 meters. So I'm just going to run it before I save it, and just run. So I'll run it like that. It's going to take some time when processing. So you're going to wait for it. So it's almost finishing. Very good, very good. It's doing something. So I'm just going to be a little bit patient. Good, and it's complete. So I can close here. And I'll just wait for it to render. It's rendering the raster file here. Very good, and there it is. So I can have my district there on top, but the visualization is not that good. So I'm going to perform some visualization here. I'll just double click and go to layer properties. Under layer properties, I'm interested in the symbology. Then under here, I'm interested, I can pick something that is inbuilt. Can pick single band pseudo color. Then on the color ramp, I'll click here. I can say I need, or I can say create new. Then I can pick catalog CPT city. Then I select OK. So I'll come here. My data is about rainfall, so I'll go with precipitation, and I'll just pick one of these that makes me happy. Let me go with that. Right, rainfall is okay for me. Then I'll just select OK. I'll come here and just hit classify like that. So there it is. Then I'll click on apply and OK. So now you can see that the visualization is much better. I'll just perform some layering techniques and have it there. Now, statistically, one might say the rainfall for this particular district will be determined only by this. And somebody else might say that the rainfall for this particular area might be determined by this and this. For the same case here, statistically, if you were to find the rainfall for this particular area, then it means that this rainfall station will not be taken into account because they fall outside the study area. But in geography, we know that this is not true. You can argue that the rainfall for this particular area will be contributed by this, either by this, and these rainfall stations. And that is why whenever I'm analyzing data that has spatial temporal phenomena, I like using geostatistical techniques. So for this particular area, you can see that for this area, the rainfall has been contributed by this station. You can see there's this contribution from this station. You can also see that there's some contribution from this station here, then contribution from the main station here, then also some contribution from this station here. The same thing applies if you look at Gomole district here. The rainfall for this district has been contributed by this station and this station here. So you can see that there is the contribution from this rainfall station and this rainfall station. Right? Now, when you come to this particular district here, you can see that we have contribution from this rainfall station. We have contribution from this rainfall station and also contribution from this rainfall station here. I can also see that there is also a contribution from this rainfall station here. So guys, that is how interpolation works. Now the next item for me to do is to now run raster statistics. So I can see if I just use my identify tool, I'll just click on the identify tool. You can see, let me just first click on this. It has a rainfall of 54.49. So 54.49, I'll just minimize it a little bit. And click here. So from 54.49 I have 54. As I'm moving away, you can see it's now decreasing. It's now decreasing from 53 to 52, 51. As I move further away, it's 50, 49, and all that. Also, if I try to move this other area, you can see that it's 53, 53.1, 52, and all that. Same thing when I move like this, it's 54, 53, 51 as I move. Now, something case for if I just select this, let me have with the Abelo here. It's 55.89. So as I move away, let me just highlight my raster. When I'm moving away, it's 54. 53, 52, 51, 49, 49.6, 49.9. Now we have some boundaries here, some virtual boundary here. Now the value for this town here was 55, and for this is 54. So as you move away from Yabelo, it decreases, and as you move close to Telltale, you should be able to see it increasing from 53 back to 54 here. So that is the concept of interpolation, and that is how we interpret interpolation. Now, we haven't completed our task yet because we need to calculate the average rainfall for each of this particular district. And this data, we have tried to use interpolation to predict values of areas or locations that were not sampled, or where samples were not taken. So I'll just close this and close that. Come back to layer. I'll go back to processing toolbox, then I'll select, I'll come here and type statistics. Now we have let me go with raster. Right, so I have zonal statistics here. So I'll just run the zonal okay, we have layer tools. I'm interested with the so I'll go with zonal statistics. So that is under raster analysis. So I'll click on this. Then I'll select my raster layer. Okay, it's already selected, but it's always good to just make sure that it's the one that has been selected. Then for my vector is the polygons. So I have to select districts. These are the various districts. Then I'm going to do just an RF under column prefix. Then under options, I'll come here and pick what I need. Okay, for my case, for the rainfall, I just need mean. But I can also be interested with standard deviation and variance. So I have mean, standard deviation, and variance. So I'm going to click on OK. Then I'm going to run. So very good, it has completed. So what we are going to do, we're going to close this and open the attribute table. Yes, and you can see that we have the mean, precipitation standard deviation, and precipitation variance. So after we have gotten this, it's fairly simple. I can these are the interpolated rainfall values for these districts here, right? So I can still copy all of this and have it in Excel. And have copy. So I can come to my Excel here. Maybe I just have a new sheet like that, and there. I now have the rainfall for the various districts. I might get rid of this. Good. I can rename this to district. Alright, so there I have So, and that is that. So the same technique can be used when you are working with other types of data that has a spatial-temporal phenomena, such as for the analysts who work with food and nutritional data. You can still do the same for your food security indicators if you want to basically aggregate them to administrative units or to regions. You can still use the same technique, like for food consumption score, the coping strategy index, and all that. You can still do the same and pre-aggregate your values to administrative levels. So that is that, ladies and gentlemen. So for your exercise, I'll recommend that you work with the food security and nutritional data to just come up with this. So ladies and gentlemen, thank you for watching and see you in my next video.